So he's in UF, Universidade Federal Fluminense. He has been working on quantum communication, especially high-dimensional quantum communication with structured light for many years now. And he's leading a very nice project in Rio, the Rede Rio Quântica. I guess you are going to mention that. So yeah, thank you, Zela. It's a great honor to have you here.
Okay, thank you, Rafael, for the nice introduction. It's also a great pleasure and honor for me to be here and to have the opportunity to talk about this very appealing and interesting subject, which is related to the use of photonic devices for quantum communication, and especially to take advantage of high-dimensional or many degrees of freedom that you can use to encode information, and not only classical, but also quantum information in a photon, in light. So this is what our lectures will be talking about, especially about what we call structured light, which is some new ways that we can encode information and control the properties of a light beam, even in the very faint single photon level, okay? So, I work at the Fluminense Federal University, which is a university in the Rio de Janeiro area. So what we see here is the city of Rio de Janeiro. Okay, so this is the Atlantic Ocean, and this is the Guanabara Bay. That's the entrance of the bay. And in this side of the bay, we have Rio de Janeiro with the Catholic University, the Brazilian Center for Physics Research, the Military Institute of Engineering, the Federal University of Rio de Janeiro. And on the other side of the bay, there is the city where we are located. It's called Niteroi. And actually, we have another federal university over there, which is the Fluminense Federal University. For those who do not understand what this word Fluminense stands for, it actually comes from the Latin. So the word for river in Latin is fiumen, okay? So that's the same, it's the origin of the word. For example, in French, fleuve for a river. So actually, we call Fluminense everything that refers to the Rio de Janeiro state. So this is why the university is called Fluminense. It's a federal university, but not from the city of Rio de Janeiro, but from the Rio de Janeiro state, okay? So I show you here, actually, this is a sketch of the project that we are building to connect the quantum optics lab in the Rio de Janeiro area. So we have a link between the Catholic University and the Rio de Janeiro Federal University, which is in straight line about 13 kilometers long. Another link between the Brazilian Center for Physics Research and the Catholic University also, which is a little bit less than 7 kilometers. The Military Institute is very close to the Brazilian Center of Physics Research, and actually they are less than 1 kilometer apart. So this is the easiest link. It's a very interesting one because we will be able to do both, to do fiber connection and also free space connection, okay? And our university here, Fluminense Federal University, has a direct view from the top of, to the top of the Brazilian Center for Physics Research, and we have 2 labs that now are equipped with telescopes, and we are exchanging signals between the 2 labs, okay? So this is a sketch of what Rafael mentioned, the Quantum Rio network, or Rio Quantum Network, that we call in Portuguese Rede Rio Quântica, okay? So this is our research group. So at this side, we have the quantum optics people. So I work in the lab, Antônio Zelaquett, Carlos Souza, Gabriel Bier Alves, and Daniel Tasca. We are experimentalists working in quantum optics with the structured light, both in nonlinear optics and also in parametric down conversion, intracavity or free space. Okay, so we deal with parametric, optical parametric oscillators and spontaneous parametric down conversion. Khaled Deishum is the theorist working on quantum optics. So he is a specialist on open quantum systems, okay, and bosonic systems, bosonic noise. So this part of the group is the condensed matter part. So Marcelo Sarandi, Tiago Oliveira, and Mohammed are the people working on quantum information applied to condensed matter systems. And here we have Daniel Brody and Daniel Jonathan, who work on the foundations of quantum information. So they are basic quantum information people, okay? So the research line is in our laboratory, so it's a picture of our laboratory. Essentially, the main subject that we investigate is the subject that we call structured light, and it involves the production of optical vortices by holographic techniques. We use these vortices or these structured beams to drive nonlinear processes, second harmonic generation, three-wave mixing, okay, parametric down conversion. So in the quantum regime, we investigate what are the consequences of this structuring of light to quantum entanglement, especially in spontaneously produced photon pairs by parametric down conversion, okay? And also, in the intense regime, we investigate optical parametric oscillators, which are essentially parametric down conversion process performed inside an optical cavity. So it's a completely completely different physical situation. And from the theoretical perspective for quantum information, you switch from discrete variables to continuous variables encoded in the quadratures, the canonical variables of a quantized field, okay? Now, the main interest from the technological perspective is the application to quantum communication. So in quantum communication, we study these processes and the use of structured light in quantum cryptography, okay? And we want to apply this to this knowledge to the project that we are developing in this quantum network that is being built in Rio de Janeiro, okay? So more information you can find in these links here. So a summary of what we are going to talk about essentially involves, to start with, quantum information. So what we understand as quantum information is to encode and to be able to encode and to process information in physical systems that are governed by quantum mechanics. Okay, so this is the essential. So it can be a spin-half particle or photon polarization. It can also be the quadratures of an intense light field, okay? The basic quantum information unit in the discrete variable approach is the qubit. So essentially a physical system, a quantized physical system that can present itself in an arbitrary superposition of two basis mode, okay? Two basis states. Now, how do we deal with this? So we can operate in these qubits by unitary operations. So these are the quantum gates that you probably studied about in courses on quantum computing. And also, you have the possibility, of course, At some point, the information will become classical, and this point is when you measure it. So then an outcome is expected to be 0 or 1, so two regular classical states, but these measurements, for example, can be a POVM or projective measurements or any kind. So what are the informational advantages? So why quantum theory brings us any advantage to deal with quantum information? So essentially, the advantage comes from two main properties of quantum systems, which are the possibility to prepare superpositions of states, okay, to use superpositions, states of superposition, and one which is related, the second one, which is related to the first one, is not the same, but it's related to, which is entanglement. So the possibility to entangle and to have non-local correlations that go beyond the correlations that are allowed by classical statistical theories, okay? Now, what these advantages can be used for? They can be used, especially the superposition principle can be used for quantum cryptography. So if you want to share a secret key, okay, you can use superposition states and to encode information and to do cryptography. And we'll talk about that more precisely soon, okay? And also to do teleportation. Teleportation is also a very important process in which you are able to transfer the quantum state from one system to another system that is remote to the first one, okay? And this is very important if, for example, you want to do quantum computing, distributed quantum computing. So if you want to access a remote quantum computer and you want to send a quantum state to this computer. Now, as I said, the platforms for quantum information processes are many. So you have photons, you have trapped ions, superconducting circuits, okay? More general condensed matter systems that you can use, for example, qubits encoded in solid-state systems. Also, the main point here, the main challenge related to these platforms is to control the coherence. So the problem, essential problem in quantum information process is that these superposition states, they don't live very long. In most, especially in condensed matter system, they decay very fast to a regular coin-like distribution, okay? So these superposition states, they are very, very fragile and they decay fast. So this is the advantage of encoding information in photons, that the superpositions for photons are long-living, okay? For example, nowadays you can produce a laser beam whose phase is well established over distance like 100 kilometers, okay? It means that a single photon of this laser has a coherence that stands over space over this kind of distance, okay? This order of magnitude. Now, our daily bread. So what we do here in our lab, is to use the photonic degrees of freedom to encode and to process information. And with the present technologies that we have to shape the wavefront of a light beam, we have many possibilities for encoding and for measuring information on a single photon, okay? On a single photon. So, the outline of the lectures is this one. So today we are going to talk about the quantum communication basics and essentially to mention two main aspects of quantum communication that I have already talked about, which are cryptography and teleportation, okay? And on lecture 2, we are going to describe what we understand as a structured light and how we can use this structured light to encode information, okay, on photons. And finally, we are going to give you an example of what kind of advantage we can obtain by encoding quantum information in this kind of system, which is the structured light, with beams in which I can shape the wavefront, but not only the wavefront, but also the spatial distribution of the polarization over the wavefront, okay? So it's not only a scalar or a phase modulation, but also a polarization modulation on the wavefront of a light beam, okay? So let's start with the basics of quantum communication. Let's talk about cryptography and start from the historical perspective, okay? So the first example of cryptography protocol that we have in history is the Caesar cipher, okay? Which is called this way because it was the way that Julius Caesar used to communicate with his military leaders, okay? To pass information instructions, military instructions. So also, it is mentioned, this kind is mentioned in the Kama Sutra because it was a way for, it is a book devoted to form lovers, huh? Okay? So how to communicate in a secret way. The lovers could communicate in a secret way, okay? So these are two examples of this kind of cipher, which is essentially involves the following. So suppose you have an alphabet, the original alphabet, the standard one, and the cipher alphabet is constructed by scramble the letters in the original alphabet and establishing a relationship one by one, okay, one to one. And then when you have an original text like this one, your secret is your prisoner. What you do is this cipher text, you replace each letter by its equivalent in the new alphabet, and you produce a sequence of letters that cannot be understood, okay? Only those who know what the alphabet, what the cipher alphabet is, will be able to decode what is being written there, okay? Well, this is the main idea. This kind of encoding survived for many centuries. So I talked about the Kama Sutra and also the of Julius Caesar. So it's a long way, okay? But now, around the 9th century, this guy here, Al-Kindi, okay, an Arab thinker, he found a way to break this kind of encoding. It was essentially, he realized that that every language has a fingerprint, which is the frequency of occurrence of each letter in that language, okay, in a text on that language, in that language. So he started to make statistics. So you take a letter, you take a text, and you build up a histogram in which you quantify the occurrence of each letter in this text, okay? And this is the fingerprint of the language. For example, This histogram is the typical histogram for English. Okay? And then what you do to decode the Julius Caesar, the Caesar cipher, is to take the ciphertext and build the same histogram. And then with that, you can guess that the most common letters in the language should be taken to the most common letters in the text that you are trying to decode, okay? And actually, there is something interesting that the decoding, this decoding is a very nonlinear process in the sense that when you start to decode, it's very slow. But once you figure out a few letters, then it goes very, very fast. So he could actually break this kind of encoding by using this kind of frequency analysis. So actually, we have here this encoded text, and by applying this frequency analysis, what you get is the decoded text, which is part of the 1001 Nights, the Tales of the 1001 Nights, okay? So what is interesting, quite interesting, that Al-Kindi broke this kind of encoding, of cryptography, in the 9th century, and people in Europe continue to use this kind of encoding. And actually, it cost Mary Stuart's head, because she used to conspire against the Queen, and this conspiration was done by exchanging messages encoded with the Julius Caesar, with the Caesar cipher. But Elizabeth had very good counselors. They knew Al-Kindi's method, and that's how they caught the conspiration, and it cost Mary Stuart's head. Now, the point was, this very, very, very interesting point is that, okay, there is in history, there is a big fight, a big dispute between crypto analyzers and cryptographers. So these are two sciences that they dispute a lot, and from this comes the development. Now, in the 16th century, we get Blaise de Vigenère introduce for the first time, the concept of doing cryptography with a key, use a key to do cryptography. So essentially, what he does is the following. Now, instead of a single changed alphabet, you take a whole list of alphabets like this, okay? And you choose a key, for example, Peter, okay? And what you do is you will use the letters of the key, and you will use only the alphabets that start with these letters. So, Peter, so we have E-P-R-T, okay? And the idea of the encoding method is the following. You have the original text, your secret is your prisoner, and then you repeat the key under, the letters of the key under the original secret, and you use, for each letter, you will use a different alphabet, and the alphabet that is being used is given by the key. And then with this, you obtain the ciphertext. The point is that with this method, the same letter can be translated to different encoded letters. And different encoded letters can be translated to the same letter. So this breaks the frequency analysis as a possibility to break the cipher, okay? So this is the first time the concept of encoding with the key was introduced, okay? Now, it's very complicated to break, very complicated to break. And in order to break this, an idea was only came up in the 19th century, so around 400 years later. And the main point, what is very interesting, is that at this point, they realized that the only way to deal with this kind of encoding was to mechanize, or use an automatic system to process information. And then comes this name here, Charles Babbage, which proposed a precursor of a computer, okay? So it was a hell of a machine, mechanical machine, to process information and to break this kind of encoding. And then, actually, from this point on, this is how computation developed. So a machine capable to process information was first conceived to break a cryptographic scheme, okay? So then it evolves to the time of the Second World War, where there was this German machine, the Enigma, that was used for the German generals to transmit orders, okay? And actually, you see, it's an electromechanical device that scrambles a text with a very complicated scheme. Now, you see, the machine was more or less the size of a regular computer or of a typewriting machine. And to fight against this, we have the name of Alan Turing. So probably all of you have watched the film Imitation Game. Is the history of this device here. Is a big machine called bomb that was developed to break the enigmas encoding. Okay. So now, how do we use the idea? So then comes as a technique for encrypting messages, goes one step further, okay? So they started at that point, also in the British secret information government, okay? So they started to use mathematics to encode information. And what is the basic idea of encoding information using some mathematical operation? So essentially, let's suppose that you have an original text that is converted to a binary sequence by the use of the ASCII table. Then you get this is the original text, and the idea of using a key is still the method to encode information, but now what you do is you take your key will be also a binary sequence, and you take the addition modulus 2 of each bit of the original text with the key, okay? And then you get a ciphertext. The point is that this kind of modular operation is a mathematical operation that cannot be inverted. You cannot invert this mathematical operation without knowing what the key is, you know? So if you add again the same key to the ciphertext, you obtain the original text. But in order to do that, you must know what the key is. Because, after all, you see, this ciphertext, this cipher sequence here, it can be produced by different original texts and different keys. So if you only have this, you cannot come back to the original text without the key. So this is the main idea in the encoding method, okay? So the main point is now what comes, so you have to worry, what you need now is to worry about the security of the key. So you need some way to exchange the key between two communicators in a very efficient and very secure way. And that's how quantum cryptography comes into play, okay? So we start to talk about quantum cryptography, which is essentially a means to build a binary sequence using qubits, okay? And this is what we are going to talk about. So, you have already been told that in a classical information system, you encode bits. So these logical zeros and one, they are actually physically, they can represent, for example, the two voltage levels in a given electrode, for example, okay? Like this one, 0 volts means zeros, 5 volts means 1. That's how the classical computers work, usually. Now, the qubit, for qubits, you have a quantum state in a Hilbert space. For example, if it's a qubit, then we are talking about a Hilbert space of dimension 2 with two basis vectors, 0, that I label 0 and 1. Physically, it can be two polarization states, two independent orthogonal polarization states of a single photon. It can be two angular momentum states of a spin-half particle, okay? Or any kind, or two independent or orthogonal states of any kind of physical system, quantum system, okay? Now, these states, since alpha and beta, the coefficients used in these superpositions are complex numbers that are constrained by this normalization condition, okay? With the degrees of freedom that are left to you to represent the state, you can represent the state geometrically on the surface of a sphere, which is called the Bloch sphere for people working in spin particles, okay, spin-half particles, or it is for us, for people of optics, it's called the Poincare sphere, okay? Now, how does the quantum key distribution system work, okay? So essentially, you have two communicators, Alice and Bob, and they want to build a binary sequence, okay? A binary sequence that they are going to use as a key for encoding information, okay? So essentially, what they do, they will, for example, in this kind of protocol, first proposed by Bennett and Brassard in 1984, you have, the idea is to transmit from Alice to Bob a sequence of photons, single photons, okay? And the bits, or the qubits, were encoded in the photon polarization. The point is that each photon can have, for example, Alice is going to send photons that can be prepared in one of 4 possible states, and these 4 states are, for example, horizontally polarized, vertically polarized, diagonal or anti-diagonal, okay? Now the main point here is that, so she's going to send one of these four states randomly. She has, for example, she takes 2 coins, and one coin will decide whether she's going to use this basis, HV, or this basis, DA. And then the second coin will be used to decide which state in that basis she's going to use, okay? So she can in this way, randomly choose between these 4 polarization states and send single photons to Bob. Bob, on his side, is equipped with polarizers or with a polarizing beam splitter, which is essentially a cube device, an optical device that sorts the polarization, the photons, according to their polarization. So if the photon arrives at the cube with horizontal polarization, it is transmitted. If it arrives at the cube with vertical polarization, it's detected. So he puts, and then he will be able to measure what was the polarization state that was sent by Alice. But he will only measure the state with 100% probability, efficiency, if he has his measurement device, his polarizer, adjusted to measure at the right basis. He can also change his polarizer. He can do that by either rotating the polarizer by 45 degrees, or by preceding the polarizer with a wave plate or a device that rotates the polarization by 45 degrees, okay? And in this case, he would have a second setting for his measurement device, a setting in which he would be projecting in this basis and not in this basis. So Alice has 2 choices to make. She chooses the basis and then the state and sends to Bob. Bob has 1 choice to make. He chooses the basis that he's going to use in his measurement device, okay? Now, the point is that if Bob chooses, adjusts his measurement device with the same basis that was chosen by Alice, then his detection will be, he will detect the bit sent by Alice with 100% probability. So if, for example, suppose that Alice sends Bob a horizontally polarized photon. So polarization, this means the bit 1, okay? If Bob sets his polarizer or his device to measure in this basis, HV, then he will get 1 with 100% probability. But if he chooses the wrong basis, then he's going to get 0 or 1 with 50% probability, okay? So in this case, if he chose the wrong basis, he cannot say anything about what Alice wanted to send him, okay? And this is a key point here. So what they do like this. Alice makes a sequence of choices, or sends Bob a sequence of photons with these choices here. She chose HV and sent V, which is 0, plus minus 0, and so on. Okay, so this is the sequence of the of the basis and the polarizations or the bits sent by Alice. Okay, and Bob, on his side, he made a sequence of choices for the basis. Okay, and he obtains a sequence of bits as a result. The point is that after transmission, they will talk to each other publicly, and they will share the information about the bases only that were used. Only the bases, not the choices that they made, not the results. So Bob is going to tell Alice publicly what was the basis that he used to measure each photon, but he's not going to tell publicly what result he obtained, of course. And then she will tell him in which cases he did the right choice. So at that point, they dismiss all the results associated with the wrong choices made by Bob, and they only keep the results for the correct choices, okay? Because they know that in these cases, they can be 100% sure that Bob detected what Alice wanted to send him. So you see that in average, they will waste 100% because this good match, this matching between bases will happen only in average at 50% of the time, okay? So they will waste 50% of the photons and only keep the other half. But for this half that they kept, they can be 100% sure that they share, they agree with the results. And if they want, for example, to build a sequence with 1,000 bits, okay, they will need to use, in average, 2,000 photons. Yes?
This might like a trivial question, but why don't doesn't Alice share the basis with Bob a priori before the measurements?
Before the measurements. Okay, good. It's a very good point. But we'll talk about this point on the next slide, okay? So, what's the advantage, okay? What's the advantage of using this method? After all, where is the security? What if someone in between try to measure the photon and resend the photon? So measure and resend the photon to Bob, okay? What's going to happen? So the point, suppose that you cannot, that there is someone, an eavesdropper, that we call Eve here, okay? And she wants to try to figure out what is the message or the key being transmitted from one to the other, from Alice to Bob, okay? And then what happens is that there is a theorem, the no-cloning theorem, that forbids you to clone, okay, to reproduce the same quantum state in an auxiliary system. So someone gives me, I have, for example, you send me a photon, I have a second photon here, and I want to reproduce the state of this photon that you sent me on this photon that I have here without destroying the original state, okay? So you can only do that if you know beforehand which basis the photon was prepared, okay? So you cannot reproduce with 100% probability a photon, a quantum state among a set of non-orthogonal states. So if Alice was sending to Bob only H or V, then Eve could just, she knows that only H or V are being used, so she could clone this, no problem. But if H, V, diagonal, and anti-diagonal are being used, then she cannot reproduce all four states. Of course, if she knows beforehand what is the basis, then she would have a polarizing and use the polarizing for each set. So it's very important that the basis is determined in real time, along the transmission, okay? It's very important. So, what if she's very, how can I say, she insists and she tries to do that. What happens is that she introduces errors. Okay, she introduced errors. So there will be situations in which Alice and Bob, they use the same basis, but they got different results. They get different results. Actually, this is not only a problem of being, how can I say, of being spied. It can be also any kind of noise, okay, any kind of noise source in the channel that randomly change the polarization of the photons that are being transmitted, okay? So actually, this process is able not only to, it's able to, how can I say, evaluate the quality of the channel. And this is very important, okay? This is a key point of quantum cryptography, okay? And so what they do, okay, they use some test bits, some photons, to test the channel. In this test phase, they are going to, Alice is going to send Bob a sequence of photons, doing her usual random choice between basis and result. Bob is going to measure, also doing his random choice of basis, and then they will publicly share not only the basis, but also the results. Because they are not going to use the bits that are going to come up from this process, they are not going to use this to build a key, okay? They are going to just test the channel. So what happens here is that, so they share both the basis and the results. And if the channel is not good, is not faithful, then there will be situations in which they will use the same basis, but they will get different results. Okay? So any attempt to detect the photon in between and resend it will introduce errors. And this is the strength of the method. Okay? Now, we have, I said that we have, so at this point, in this this protocol, the BB84 protocol, we used one of the quantum mechanical aspects that gives us informational advantage with the superposition. So the point is that 45 polarization state is a superposition of horizontal and vertical, okay? And at the same point, at the same time, it's a superposition. So if I choose one basis, the HV basis, the result for measurement, the result is random. But if I choose the right basis, the diagonal anti-diagonal, then the result is certain. Okay? So we are using the superposition principle to provide security to the communication. Okay? Now, how can we use entanglement? Okay? Now, entanglement, I said that was the second quantum feature that could be used to give informational advantage in the communication system, okay? Now, what's entanglement? So, we know that we combine, when we have two qubit systems, two quantum systems of dimension 2, we combine their Hilbert space, making a tensor product. So we have the tensor product states, and in this, we have the tensor product space, and in this tensor product space, the interesting thing is that although you can build a basis of the of the combined space by simply doing the tensor product of the basis of each individual space. In this new space, the combined space, there are states that cannot be factorized as a tensor product. And this is the origin of entanglement, okay? So entanglement has definitions, general definitions for mixed states and so. So what I'm presenting here is the basic definition for pure states, okay? So whenever a quantum state that lives in the combined space of the two qubits, whenever it cannot be factorized in this way, okay, we say that the system is in an entangled state. Now, if we use the tensor product basis, like we had 0 and 1 for qubit A, 0 and 1 for qubit B, so the new basis will be this, 0, 0, 0, 1, 1, 0, 1, 1, and we build an arbitrary superposition, okay, with coefficients alpha, beta, gamma, and delta, okay? Now, we know that for pure states, the concurrence, which is this quantity here, okay, which is this quantity here, can reveal whether the state is entangled or not, whether it can be factorized or not, okay? So for product states like this one, okay, this quantity here would give 0, would be 0, okay? So it's a very easy calculation that you can compute. Now, you have also partial entanglement, so this quantity here can be varies continuously between 0 and 1, and when C is equal to 1, we have what we call maximally entangled states, okay? And examples of the maximally entangled states are the so-called Bell states, okay? Actually, these four combinations here, 0, 0, plus or minus 1, 1, and 0, 1, plus or minus 1, 0, these four combinations, they are maximally entangled. So if you compute the concurrence for these states, it will give you 1. They are also mutually orthogonal to each other. So the combined spaces of the two qubits admit a basis of maximally entangled states, okay? For example, a basis of Bell states. So this is the basics of entanglement. And now, let's, in this combined space, consider a few operators. I told you that the tools that we have at hand to deal with quantum information for quantum communications are quantum states and the physical quantities that are quantum operators, which we can use to describe measurements or which we can use to describe unitary gates, unitary transformations, okay? So let's consider the three Pauli matrices, okay? Sigma X, Sigma Y, and Sigma Z. And Sigma Z is the diagonal one, so the basis, the single qubit basis is naturally the basis of eigenvectors of sigma z with eigenvalues 1 and minus 1, okay? And the sigma x is the flip operation, okay, that makes 0 goes into 1 and 1 goes into 0, okay? Now, we can define also the eigenvectors of sigma x, okay, which I call this way, 0x and 1x. They are combinations of the eigenvectors of sigma z, and also sigma x, as all Pauli matrices, they have eigenvalues 1 and minus 1, all right? However, note that sigma x and sigma z do not commute, which seems that they are not compatible. They cannot be measured simultaneously. There is no state where you can get 100% probability for measuring both of them, an outcome of both of them, okay? So the point is that when you combine two systems, two qubits like that, okay, two qubits, these operators will play a very interesting role, the combined operators of the two qubits, of the two Alice. So let's suppose you have qubit A and qubit B, okay? In our case, we are going to consider that Alice and Bob, they share a pair of qubits, okay? And what happens is that we see that they will share a pair of qubits, but not in an arbitrary state. They will use this kind of state here. So it's one of the Bell states, 0, 1, minus 1, 0, over square root of 2. Okay? If we talk about a pair of spin-half particles, okay, this is the singlet state, the singlet state. If you remember from your basic quantum mechanics course, the singlet state is the state with total angular momentum equal to 0 for a pair of spin-half particles. So you combine a pair of spin-half particles. The total angular momentum can be 0 or 1. For 0, you have only the singlet states. For 1, you have all the triplet, okay? But for 0, you have only the singlet state. Now, if the angular momentum is 0, the eigenvalue of J squared, the total angular momentum squared, okay? If it's 0, then any component of the angular momentum must be 0. So actually, this combination here is also a singlet state for sigma x. Okay? So in any situation, or at any direction in space, if you write this state here in terms of the eigenvectors of any component of the angular momentum for a spin-half particle, or for any combination of the matrices, sigma x and sigma x, or sigma z and sigma z, okay? What happens is that you always have this kind of anti-correlation. If one bit is measured at 0, if one qubit is measured at 0, the other one is measured at 1. And it doesn't matter what direction you are measuring, okay? So the point here is that no matter if Alice and Bob, they share a pair of qubits prepared in this kind of singlet state, either if they measure either sigma z or sigma x, they will obtain opposite values. They cannot obtain both 0 or both 1. It doesn't matter whether they choose. The only thing is that this correlation will be seen if they both measure sigma x or if they both measure sigma z, okay? Now, this is how they are going to build the key. They are going to measure the operators, the same operator. Whether, let me go one step back here. Note that if they share this state, of the two qubits prepared in this state, and they decide to measure always sigma z, okay? At each measurement, it's not, they will randomly obtain 0 or 1, each one of them, but they will be 100% sure that the results they obtained are opposite one to each other. So they make the measurements, a sequence of measurements. Alice will have a sequence of results, of bits. Bob will have his sequence of bits, but he only needs to flip each bit of in his possession, okay, to obtain the same sequence as Alice. And they will certainly share the same binary sequence. But now, how can we be sure that this is a secure way for sharing a binary sequence? So essentially, we try to see what happens if a third part, an eavesdropper, wants to take information from what is being shared between Alice and Bob, okay? So suppose that Eve wants to obtain information about the key that is being exchanged by Alice and Bob. So what happens is that somehow, if she wants to get information on that, because now Alice and Bob are not sending anything. They are not sending anything. They have pairs of qubits. The qubits could be there, be prepared long time before the communication started, okay? So they are not sending anything. So if she wants to obtain information, she needs to entangle a qubit in her possession with the qubits of Alice and Bob. So what happens is that, assume that we have a general state of 3 qubits, Alice qubit, Bob qubit, and Eve's qubit. Now there are 3 qubits in play here. One is the qubit Eve has, and the one that she's trying to use to obtain the information from the state shared by Alice, or the results obtained by Alice and Bob. So what happens is that if this qubit, if this state is an eigenvector of sigma z times sigma z with eigenvalue -1, and Alice and Bob can test that by comparing their results, okay? They measure sigma z many times, okay? And they see that they have opposite results, so it means that the product sigma z of Alice times sigma z of Bob has an eigenvalue which is -1. But if this kind of correlation is observed, then it means that the state, the 3-qubit state, must be of this form. It cannot have this kind of component or this kind of component, because this would give the same result for Alice and Bob. Is that clear? Okay? No? Yeah? Okay. So by testing this kind of correlation, they rule out these 2 parts of the state, of the quantum state. And then this one, only this possibility is left. However, this possibility breaks the correlation for measurements in sigma x. So they make measurements in sigma z to rule out a part of the state, of the 3-qubit state. Now, if they test also for the sigma x correlation, then for the sigma x correlation, you can show that this cannot be true, okay? So the only way that the 3-qubit, the one by Eve, Alice, and Bob, the only kind of state that could be consistent with correlations both at sigma z and sigma x would be this kind of state. This can be shown, okay? All right? So it's very easy. So if you want, you can recall that actually you can go back to the and make the product here, and then you see that, so change these 2 states here, write them, these two here, write them in terms of the eigenvectors of sigma x, okay? And then you see that if there is, if you plug these expressions here at 0 and 1 1 and 0, then you will see that this kind of state will produce the possibilities with 0, 0 at sigma x and 1, 1 in sigma x. So actually, if they measure both the anti-correlations, okay, both at sigma z and sigma x, then they can be 100% sure that if there is a third party with a qubit, this qubit of this third party, this third qubit, is factorized. If it's factorized, it cannot share any information with the main qubits, with the qubits that Alice and Bob are going to use to produce the binary sequence. Is that clear? Okay. Yeah, sure.
So if we measure the anti-correlations of both lasers, they have -1. They have that gives them one trying to eavesdrop, they don't have any information, right? So the way that they would detect the presence of would be by observing that this anti-correlations were different from -1.
Yeah, so there is, okay. So there is this, how can I say, this step of testing the channel in which, because when they are sure, 100% sure about the security, they will make the measurements, they will not communicate the results, okay? But to test the channel, what they do, they make measurements at sigma z, they make measurements at sigma x, and they share what they measured and what the results were. And then they will figure out that if there is a third party that is entangled with their qubits, then they will get incorrect results. They will get correlations instead of anti-correlations. They will get not correlations, but they will get random results. They can be both 0, 0, 1, or it doesn't matter, okay? So the point is that any entanglement with a third part would spoil the anti-correlations, and they have to make a diagnosis of that by sharing both what the measurement that was done and the results that were obtained, okay? So that's the basis of the security of the protocol. Yes, sure.
Instead of singing it, we use other three bell states. Will the security of the protocol still remain? And you have to change the correlations to it.
So you mean if, you mean if, for example, if the qubits of Alice, Bob, and Eve are like GHZ, for example. So this would be the worst scenario. Alice and Bob, they would get completely random results, completely random. So yes, yeah. No, okay, I understand. So you mean if here, instead of having minus, I get plus, yeah? So the point is that it could be done also, and actually it could be done at any, you could use any one of the 4 Bell states, okay? Or any maximally entangled states. The only tricky part is that if you use a different state, the measurements will be different ones, okay? So in this way this is the easiest case for you to figure out what the good measurements are, okay? Yes, please.
There are any protocols to factorize or something like that, third qubits when you are partially in entangled states? Because the curve we have here is for massive.
Okay. So actually, there is okay. If you first, let's think about a second 2 qubits. Okay, if you have only 2 qubits and you have a state that is not maximally entangled, okay, there is a process called entanglement distillation. Entanglement distillation is some kind of partial measurement that you can make, the both parties can make, in order to continuously project the original state into a maximally entangled state. For example, you could do a Bell measurement. So it's a joint measurement that projects the two qubits in a Bell state, which is a maximally entangled one. So what you are saying, what I can tell you is that, okay, if there is some third part that is entangled, what Alice and Bob could try to do is to make Bell measurements, okay? And then they would get a maximally entangled state. But the point is that it would be random, the result would be random if they are entangled to a third party, all right? Any other questions? Okay, so, okay, I have already mentioned that. So now, that's the main sequence, okay? This is how the protocol works. Alice and Bob, they will sacrifice some qubits to test the channel. If Eve perturbs the state, the correlation is violated and she is detected. The correlations, both at sigma x and sigma z, they are violated, and they can figure out that there is someone on the channel, okay? If not, both Alice and Bob, they can measure, for example, sigma z for a sequence of qubits, okay? And they, when they do that, these anti-correlations that they will be 100% sure, they can now trust the channel. So the anti-correlations will make sure that if Bob flips all his bits in the results, in his sequence, he will have the same sequence as Alice, okay? And they can use this sequence to, for example, as the key for encoding secret information, all right? So their results compose an anti-correlated binary sequence. One of them, Bob, inverts their bits to obtain the shared key. Okay? I think, no, well, there is also, how am I with time, Celso? Good. I'm arriving at the end. So let's now switch to the other kind of quantum communication protocol that profits from communication protocol that profits from quantum property, from entanglement in particular, okay, which is quantum teleportation. So the main idea in quantum teleportation is the following, okay? So you have two communicators, Alice and Bob. Alice wants to send a quantum state to Bob. That's the main idea. So she has a qubit. So the quantum state that she wants to transmit to Bob is encoded on a third qubit. So Alice and Bob share a pair of maximally entangled qubit, okay? In this case, I'm assuming a Bell state of this kind, 0, 0 plus 1, 1, all right? And again, you can use any one of them. The only tricky thing is that you have to change the measurement accordingly, all right? Okay? So now they share a pair of qubits in this maximally entangled state, and Alice wants to transmit this kind of state, this state here, alpha 0 plus beta 1, to Bob. After all, the information being transmitted is composed by these coefficients, alpha and beta. She has a pair of complex numbers that she wants to communicate to Bob, okay? Now, the protocol works like that. They share this maximally entangled qubit, the maximum entangled qubits, okay? She has the quantum state to be transmitted in the third qubit, and then if we write down the quantum state of the combined 3 qubits here, okay, the 2 being shared, and the one that carries the quantum, the information to be transmitted, we write down this 3 qubit state. It looks like this, and then we can do the following, okay? I will write now in terms, I will like reorganize this 3 qubit state in this way here, okay? I will put together the possibilities for A and C, for these two here, okay? And then we have each possibility for AC with the corresponding possibility to Bob, okay? And now, the point is that Alice will take the 2 qubits that are in her possession and make a Bell measurement on these qubits. So she's going to make a measurement that projects the 2 qubits A and C in a Bell state. So now, these are the 4 Bell states, and so these are the 4 possible projections that result from Alice measurement, okay? So, now, if we do, now there is a tricky part here, okay? So these are the 4 Bell states. We can rewrite this 3 qubits state using the Bell basis for A and C, okay? And when we do that, so I rewrite the 3 qubit state in the AC Bell basis, and we see an interesting thing is that for each one of AC Bell state, there is a superposition in Bob qubit involving the coefficients alpha and beta. Okay? There is a superposition of all. So it's quite interesting now that when Alice performs a Bell measurement, a Bell projection on the 2 qubits that are in her possession, one of these 4 possibilities here will be, the outcome will project A and C in one of these 4 possibilities here. And what happens is that automatically Bob's qubit will be projected in one of these 4 states here. All 4 states, they carry the coefficients alpha and beta, okay? However, this one is precisely the state that Alice wanted to transmit. This one is the state multiplied by sigma z, because this guy here got a minus sign. This one is multiplied by sigma x, because if we look at this one and this one, we see that 0 and 1 are flipped. And this one is the product, sigma x and then sigma z. Okay? So actually, depending on the result of Alice's measurement, Bob qubit will collapse to a state which is either the correct state that Alice wanted to transmit, or this state apart from a unitary transformation. So what they have to do, and this state could be a secret state, okay? What they have to do is Alice makes a Bell measurement in A and C. And then she calls Bob and tell Bob what the result of the measurement was. So she tells Bob whether her 2 qubits were projected to chi1, chi2, chi3, or chi4. If she says that it was projected to chi1, Bob does nothing. He knows that his qubit was projected to the correct state that she wanted to transmit. Now, if Alice tells Bob that her Bell measurement projected to chi2, then Bob knows that he has to apply sigma z to his qubit in order to obtain the state that she wanted to transmit, and so on, okay? So depending on the result of Alice, that Alice communicate to Bob, he will perform a unitary transformation that will get his qubit to the state that Alice wanted to transmit, right? And is there any question about that? No, okay. So this is a summary of the protocol. Alice has a qubit prepared in a given state that she wants to transmit to Bob. Alice and Bob share a Bell state like this one, okay? Now, Alice makes a measurement, a Bell measurement on the 2 qubits that are in her possession. This Bell measurement automatically projects A and C, the 2 qubits in an entangled state. As the 2 qubits A and C are entangled, immediately the qubit B is disentangled from the other 2 and will carry the state that you want us to transmit apart from a unitary transformation. Okay? That's it, guys. So this was the idea, the main idea I wanted to pass you this first lecture. In the next lecture, we are going to talk about photons, light and photons, okay? So what are the degrees of freedom? How do we conceive them? How do we control them in the lab? So the next talk will be more shared between experimental part and theoretical part, okay? Thank you very much. Thank you.
Any further questions for Zela?
Just ask about how do you generally differentiate from an eavesdropper, or for example, just that the channel is noisy and perhaps we have the polarization to change by interaction?
It's a good question. You know what? The most honest answer to this question is that I don't know exactly. I don't know. I don't know how to do that, okay? However, I think that there is no way. However, I think that maybe there is something, these instrumental inequalities that Rafael studies. I don't know if Alice is trying to do something, maybe there is some way that you can have some hint or not, no?
Well, I mean, if you have an eavesdropper, you are going to have change in the outcomes at least 25% of the time, right? So if there is an eavesdropper, like 1/4 of your runs will be spoiled. So, and typically you need a channel that has like a low noise. So like if you are operating on a noise of 25%, it's a pretty bad channel. So you cannot see if that's like an eavesdropper or just noise of the channel. So like in this case, you have to change your channel. Mm-hmm. You have to improve it. So in general, I don't think you can pull them apart, no.
Okay.
Yes.
So, yeah. Any other question? No? Okay.
Well, so let's thank both the lecturers for the morning, and I don't know if in the afternoon there is... Okay, you should work on the exercises, yes. Okay, well, so let's thank all the lecturers from the morning session.